Okay, so for these two exercises, we want to find the canonical sum of products form for these truth functions that are given to us in these truth tables. The canonical sum of products form, I think I mentioned up above this that this is also called disjunctive normal form. And this is kind of a basic concept in circuit design or just Boolean logic that we can always write a function or a Boolean expression that represents any truth table or any function written out like this and just sort of the list of all of its possible states like these tables are doing. We can always find an expression that represents that truth table just by focusing on basically the ones here, or the states where our function is true. So to build a canonical sum of products form for this table, again, we're only going to focus on any of these rows where the function is true, and the only place where this function is true, or 1, is down in this last row where both of the inputs are 0. So we want our function to output 1, but only when both of the inputs are 0. So let me just write out this one. The way to represent that here would be not x1 times not x2, or inverted x1 times inverted x2. And the reason this works is if we start picking out certain values from our table here, we want to verify that this function produces the correct output for each of those combinations. If I plug a 1 into x1 and I plug a 1 into x2, well, the complement here, again, the opposite of 1 is 0, so we would have a 0 times a 0, and 0 times 0 would be 0, which is the output that we're supposed to get in that first row. And we can do the same thing with these other rows. And then eventually when we get down to 0 and 0 here for these two, for these inputs, if x1 is 0, then the negation of that would be 1, and that means this would also be 1. So we have 1 times 1, and 1 times 1 is 1. So we end up with the 1 that we're supposed to have in our function here. So essentially, by putting in this expression that is only true when both of the inputs are false, or only 1 when both of the inputs are 0, then we exactly represent this last row. But because we don't have anything else in this expression, there's no way for any other combination except for that exact combination of two zeros. There's no way for anything else to work in here to become 1 or to become true. So that's all we need for that. And one way we can tell that we're done is that we only have one, or we only have one actual true state in this entire function, which means we only have one term in our canonical sum of products form. And so by extension then, if we look down at, let's go to number 13 now, I see 2 1s in this column, 2 1s in the truth function of this, whatever this function is, which means I'm going to expect to have 2 terms in my canonical sum of products form. And those 2 terms are going to be added together. So we can just go ahead and say we're going to have 2 terms, and we'll explain why they're going to be added together in a minute. But the first term should focus on this 1 here, which should happen when all 3 of the inputs are 1. So when all 3 of the inputs are 1, we get a 1. And because all 3 of these are true, we can just go with the standard x1 times x2 times x3. If all 3 of those inputs are 1, then the product of all of them is going to be 1. But if we throw a 0 in there, if any of these is 0, this is now going to be false. So notice everywhere else in the entire table has a 0 in some entry. So the only time this is ever going to be true is if all 3 of those inputs are 1, which only happens in the first row. Next, for our next term, we want to focus on the other 1 in this table in the output. And this 1 is supposed to happen when x1 is 0, x2 is 1, and x3 is 1. Let me see if I can actually highlight this. Okay, so in this row, we want, let's see, x1 to be false, or for this, I guess this needs to be true when x1 is false, or when it's 0. And then x2 and x3 should both be 1. So this would be the way to represent that. I mean, all I'm doing is if there's a 0 here for one variable, then I'm going to put its negation in. And if there's a 1 in the input for that variable, we're just going to put the regular variable in. And putting all those together gives us exactly what we want. Because if we imagine, if we have this set of inputs, plugging in 0 for x1 makes this a 1, which is the opposite of 0. And then plugging in 1 for x2 and x3 makes both of these 1. So again, all three of these variables are going to be 1. And that's the whole point. One of these terms is only going to be true, or it's only going to produce a 1 if all three of these factors are 1s. And in this case, because our input is supposed to be 0, we use a negation to force that to end up being a 1. And if that's a 1 and these other two things are 1s, then we have a 1 from the output. So then finally, this should be our entire function. And again, to explain why we're adding these two things together, addition represents the OR operation. And so we want this function, let me copy this up here. Again, these are the two rows, or the two places in our function that we actually want to be true. We actually want to produce 1s. So for each of those two rows, we have a term. If we have these inputs, the product of all of these will give us a 1. And if we have these inputs, the product of all of these will give us a 1. And if this is a 1 or this is a 1, then this sum of these two terms will be a 1. So then by adding them together, we're just stacking on the different possibilities. And if we had 5 rows here that all had 1s in them, we would go one at a time, create an extra term for each one, and then add them all together at the end so that each of them individually could make the whole function true or make the whole function produce a 1. So that would be the canonical sum of products form for our table here.